Picture a wooden ship somewhere in the middle of the Atlantic in 1492. No satellites, no charts that show what lies ahead. The nearest coastline is weeks behind you, and the man in charge is not guessing. He is calculating. He knows his heading, he knows how fast the ship is moving, and he knows exactly how many hours have passed since he last had a reliable fix. The question is not how people navigated before maps. The question is how good they actually were at it. Here's the thing people get wrong about pre-map navigation. They imagine it as wandering, hoping, stumbling onto the right coastline by luck. But organized navigation systems go back at least to the 6th century BCE in the Mediterranean, where sailors were already using written sailing directions, annotated route lists, and rudimentary sea charts to move cargo and armies around an entire ocean basin. This was not guesswork. It was a structured, teachable discipline with real consequences for failure, and those sailors passed it down across generations. The default method for the vast majority of early seafarers was coastal pilotage. You stayed in sight of land. You followed the coastline. You watched for the mountain with two peaks, the river mouth that appears on your port side, the headland that juts out at a particular angle. These were not vague, poetic descriptions. They were functional route instructions that worked like a written program. When you see X, turn to Y. Medieval sailors in the Mediterranean were still using this system as their primary method well into the 14th century, even after more sophisticated tools existed. But what do you do when you have to leave the coast? That is where dead reckoning comes in. And before you picture someone squinting at the horizon and hoping for the best, understand what dead reckoning actually is. It is a continuous estimation problem. You take your known starting point, you apply your compass heading, you estimate your speed, you multiply by elapsed time, and you get a new position. Speed times time equals distance along a known direction. Columbus used this method as his primary navigation tool crossing the Atlantic. This is not folklore. His logs say so. Columbus tracked time with hourglasses and estimated his ship's speed by watching floating debris, seaweed, and water movement pass along the hull. He counted, he timed, he calculated, and then he marked the new position on his chart as the starting point for the next day. Every day was a fresh calculation layered on top of the last. The problem is that small daily errors compound. After weeks at sea, the uncertainty in your position can be enormous. Columbus knew this, so he built his strategy around hitting a target latitude first and then running along it until he made landfall. That strategy of running down a latitude is one of the most elegant workarounds in navigational history. You cannot know your longitude with any accuracy, but you can know your latitude, so you sail north or south until you hit the latitude of your destination, and then you simply hold that latitude east or west until land appears. It turns an impossible precision problem into a much more manageable one. You do not need to know exactly where you are on the ocean. You just need to know which horizontal band of the Earth you are in, and then you follow it. To measure that latitude, navigators used instruments like the astrolabe, the quadrant, and later the cross staff. All of them are doing the same fundamental thing, measuring the angle between a known star or the sun and the horizon. Polaris, the North Star, is almost exactly above the North Pole, so its angle above your horizon tells you your latitude directly. If Polaris sits 40 degrees above your horizon, you're at 40 degrees north latitude. That relationship is real physics, it is predictable, and it does not require a map. It requires a clear night and a simple angle measuring device. The magnetic compass entered European maritime practice somewhere around the 12th to 13th centuries, arriving from China through the Islamic world. And this is where most people assume the story ends. Compass equals solved. But the compass only tells you which direction you are heading. It says nothing about where you are. It also has its own problems. Local magnetic variation, interference from iron fittings on the ship, and the simple fact that magnetic north and geographic north are not the same. Experienced navigators treated the compass as one check among several, not as a single authoritative source. Islamic navigators in the medieval Indian Ocean had an instrument called a Kamal that deserves far more attention than it gets. It is a small rectangular piece of wood tied to a knotted cord. You hold the board at arm's length, align its bottom edge with the horizon, its top edge with a target star, and the knot your teeth are biting holds the cord at exactly the right length for that angular measurement. The number of knots from board to teeth corresponds to a known latitude. Wood, cord, and memorize star altitudes. They solved this centuries ago. The question is why we forgot. Now let us talk about lead lines, because this one is genuinely clever. A lead line is a weighted rope marked at measured intervals. You drop it over the side and feel when the weight hits bottom. That gives you depth. But here is the part most people miss. The lead weight had a hollow base packed with tallow, a type of animal fat. When it hit the seabed and you hauled it back up, sediment stuck to it. Sand, mud, shell, gravel. Experienced pilots knew the depth profile and the bottom composition of familiar coastlines, the way a carpenter knows the feel of different wood grain. Think about what that gives you. Depth contours and seabed texture form what we would now call a one-dimensional cross-section of the seafloor, and experienced pilots had that cross-section memorized for every approach to every harbor they regularly used. You could approach a familiar coast in complete fog with no stars visible and still know roughly where you were by what was coming up on the lead line. A specific depth reading of sandy bottom transitioning to shell gravel at 18 fathoms might tell you exactly which channel you were entering. This is not primitive. This is systematic environmental reading. Then there is Polynesian wayfinding, and this is where the story gets genuinely astonishing. Polynesian navigators crossed thousands of kilometers of open Pacific Ocean without a magnetic compass, without written charts, without metal instruments of any kind. They used stars, yes, but they also read ocean swells. Islands disturb the deep ocean swells moving across the Pacific, creating characteristic interference patterns and reflections. An experienced wayfinder could feel the shape of those wave patterns under the hull and infer the direction and rough distance of an island that was still completely below the horizon. From a physics standpoint, what Polynesian wayfinders were doing was reading wave interference patterns as a signal. Long-period ocean swells travel in predictable directions across the Pacific. When they encounter an island or a reef, they bend, reflect, and scatter. The disrupted pattern on the backside of that obstruction carries information about what caused it. A trained navigator could detect those subtle changes in swell direction and rhythm by feel, by watching the water surface, and by the motion of the canoe itself. This is an extremely refined, embodied skill built up over generations of deliberate practice and oral transmission. On land, the systems worked differently but were no less organized. Nomadic groups followed animal migration routes and river systems that formed natural corridors across terrain. Mental maps and oral route descriptions were the primary technology. Think about what oral directions actually contain: a sequence of landmarks, bearings, distances, and decision points. Sail east until the mountain with 2 peaks appears, then turn north until the river mouth is abeam. That is a functional program. It is a route description that works reliably without a map because the landmarks are stable and the instructions are unambiguous for anyone who has learned them. One of the most important things to understand about pre-map navigation accuracy is that it was calibrated to the task, not to an abstract standard. Dead reckoning accumulates error. Small daily mistakes in speed estimation or compass reading compound into substantial positional uncertainty after weeks at sea. But the navigators knew this and they designed their strategies around it. You do not need meter-accurate positioning to cross the Atlantic if your target is an entire continent. You need to know your latitude band and your general heading, and then you need a strategy for making landfall that accounts for the uncertainty in your position. Even after detailed maps began to appear in the 15th and 16th centuries, the old methods did not disappear. Portolan charts were excellent for well-traveled parts of the Mediterranean and European coasts, but entire ocean basins and interior continents remained blank or schematic on those charts for a very long time. Sailors and travelers still depended on coastal pilotage, lead lines, dead reckoning, and celestial latitude in those white spaces on the map. Even when accurate charts of other regions already existed, the old techniques and the new charts ran in parallel for centuries. The transition was gradual and messy, not a clean handover. What strikes me most about all of these systems, from Mediterranean sailing directions to Polynesian swell reading to the Islamic Kamal, is how layered they were. No single method carried the whole load. Stars backed up the compass. Soundings confirmed the dead reckoning. Wind patterns and bird behavior gave early warning of land. Each layer added redundancy, and redundancy is what made long voyages survivable when one source of information failed. That is not primitive thinking. That is exactly how good engineers design critical systems today. Multiple independent inputs, cross-checked constantly with no single point of failure. If you take one thing from this video, take the layering principle. Every one of these navigation systems worked because it combined multiple independent methods, each with different failure modes, into a cross-checking network. Coastal landmarks fail in fog, so you add lead line soundings. Stars fail when clouds roll in, so you hold your last compass heading. Dead reckoning drifts over time, so you correct it every time you get a celestial fix or a depth confirmation. The individual tools were simple. The system they formed together was robust. That is a design philosophy worth understanding whether you are crossing an ocean or orienting yourself across a landscape you do not have a map for. If this kind of practical historical engineering is what you are here for, hit subscribe and stay close to this channel. We go deep on the techniques that worked before modern infrastructure existed, and we break down the actual principles behind them so you understand why, not just what. Next time we are looking at another piece of forgotten practical knowledge that Raymond from the comments section will absolutely have opinions about. The old ways worked for a reason. Let me show you why. See you in the next one.